Hi all. We're studying rotational motion. And the way we're going about exploring or studying rotational motion is we're exploring the symmetry between translational motion and rotational motion, right? Because it's just two different types of motions, and we already said the laws apply to two. And what we're going to do in this video is we're going to apply Newton's laws, especially the second law. We're going to apply Newton's laws to rotational motion and see how it works, right? Now, we already know Newton, with his great laws, right, has put his great laws to describe motion, right? And his first law, obviously, for translational motion states that a body continues to be in a state of rest or in constant motion of uniform velocity in a straight line. It continues that way unless it is forced to change its state by a force. The same applies to rotational motion. A body which is in rotational motion continues to be in rotational motion unless that state uniform or the omega is constant, uniform rotational motion, until that state is changed by a force. The same thing applies. But I want you to think about this. Now, let's say there is a door in a hinge and you apply a force. Clearly, by applying the force, the door begins to move. You have changed the motion. It goes into rotational motion, right? Here's the same force if you apply it near the hinge, and the same force if you apply at the farther end of the hinge, just near the handle of the door. Is there a difference? Yes, there is a difference. You will find that when you apply force to the handle of the door, you're able to create a greater change in rotational motion. A greater change in omega you're able to create by applying a force at the handle rather than applying the same force at the hinge, right? Therefore, there is more to, in rotational motion, there is more to force. Yes, the counterpart of rotational motion, of force, the counterpart of force in rotational motion is what is known as torque. And this is so important. It's called torque. That is the counterpart of force in rotational motion. And let's see how it works, right? The quantity we are looking at is called torque. And the way we define torque, right, or it is defined for is torque, which is a vector, is equal to R cross F. What is R and what is F? Now let's look at the body, okay? Let's look at the body which is in, let's say, rotational motion. This is the body and this is where it's fixed, the axis of rotation is fixed, right? Now, the moment you're applying a force in the anti-clockwise direction, it begins to rotate around the axis of rotation. Now, let's say the force is applied like this, in this direction. This is the force, F, right? We look at the vector R, which is the vector from the axis of rotation to the point where the force is applied, that vector, right? In this case, sorry. This is a vector R. Okay, this is the R that I'm talking about, right? And the direction of R is in this direction. The line, okay, R, the direction of R in this, and the direction of force you're applying is here, and this angle is called the theta. So this is R cross F, right? The two vectors, the angle theta between them, we know R cross F is RF sine theta. Is the value what comes over here, and therefore RF sine theta, this is the theta that we're talking about. The angle between R and the angle between F, that is going to determine the magnitude of the torque, the effect of the force. And this is quite intuitive if you look at it, because let's say the force is applied in this direction. There is a component, the component which is perpendicular to the R, which is the point, the vector I said from the axis of rotation to the point where the force is applied. The perpendicular component of the force creates rotational motion, right? The radial component, right? The component which is in the direction, so you have F sine theta that way and F sine theta going into the axis of rotation or in the direction of axis of rotation, does not create rotational motion, isn't it? Only when you apply it exactly at perpendicular to the R, you get rotational motion is created. So that's pretty intuitive that It is, if you need to apply a greater force, you should apply perpendicular to r, to the vector r, which is the vector which is from the axis of rotation to the point of where you're applying the force, right? So here we are, torque is equal to r cross F. So torque is what is going to create a change in a rotational motion, right? And now we know that using Newton's laws, we know that the torque is going to accelerate the body, or in short, it is proportional to alpha, right? And this is a proportionality sign, or it is proportional to the angular acceleration. The torque is going to create an angular acceleration. But there is something that resists a change in motion, right? In translational motion, we saw inertia is measured. The measure of inertia is mass. Mass is what resisted that change, isn't it? The inertia of the body, which is measured in mass, is what resisted that change. So the important question here is, what is the counterpart of mass in rotational motion, right? Tau is proportional to the angular acceleration. So therefore, tau is equal to that quantity into alpha. So we find the counterpart of mass, the measure of rotational inertia, is called moment of inertia. Moment of inertia. Right? And this is such an important quantity for rotational motion. And the way you calculate moment of inertia, now it's interesting, you will see that moment of inertia, which is I'm going to represent by I, is equal to each particle. Now we know that rotational motion, and we're looking at rigid bodies, right? Rotational motion of rigid bodies, each particle into the square of the distance it is from the axis of rotation, right? The square of the distance from the axis of rotation. So m1 r1 square plus m2 r2 square, so on and so forth, right? Which is equal to, so therefore moment of inertia is equal to sigma mi ri squared, or the moment of inertia is equal to each mass of each particle into the square of the distance of the particle from the axis of rotation, right? That is what is given as the moment of inertia. Now this is the definition of moment of inertia. One may ask this, it's a question, why is it not mass into r, right? Why is it mass into r square? I want you to know that it is mass, each mass into the square of the distance, of its distance from the axis of rotation. Well, yes, we will mathematically prove this later, that it is not r alone, it is r square. Okay, right now you're going to accept the proof the way it is. I'm giving you the what it is, and we'll accept it for now, but mathematically you will see that yes, it is mass into the square of the distance, right? That gives you inertia of rotational inertia, right? So that's moment of inertia for you. So now we have torque and we have the moment of inertia, and now it's time for us to write Newton's second law. We know that for Newton's second law, in translation motion, F is equal to, I'm going to take it off right over here. So we have torque, that's tau, and we have moment of inertia, which I'm going to represent by I. Newton's second law for translational motion was F is equal to ma. Newton's second law for rotation is given by tau is equal to I omega. And there you are. Okay. Newton's law applied to rotational motion. Tau is equal to the moment of inertia. Sorry, omega here, mistake. This is alpha, which is angular acceleration. Or tau is equal to moment of inertia into angular acceleration. Newton's second law for rotation. Thank you.